With this video, I will describe the computer optimization. Optimization is extremely important in the design of a wide variety of systems. I will talk about two applications, optimization in modeling and optimization in control systems design. Parameter optimization is a procedure by which we determine some systems parameters by minimizing or maximizing a certain criterion in a transient response. The criterion function depends on the error between the desired and the actual signals and is often of an integral type. Besides the criterion function, constraints can also be included in optimization procedures. This takes into account some real properties of dynamic systems, for example, physical constraints of actuators, measurement systems, controllers, and so on. Let's explain the analytical view to the optimization problem. Criterion function is usually of integral type. If we suppose that it can be analytically derived, this means that we can calculate the criterion function as the function of the error, then it would be a function of parameters. This means that we can calculate that the criterion function is the function of parameters p1, p2, p3, and so on. Then the optimal values of parameters can be obtained by calculated partial derivatives. For example, the partial derivative of the criterion function on the parameter p1 equals 0 gives us the optimal parameter p1. However, analytical approach can be used only in very simple examples. So this slide then shows how computer optimization in modeling is actually used in real situations. Namely, we usually use a MATLAB main program for optimization, but we use also the Simulink scheme in which we model the problem. In this case, we have the model to which we want to optimize its parameters. So we have a structure and parameter optimization will define the parameters. We have also the measurements in data files, so we compare the output of the model and the measurements and generate the error signal. On the basis of the error signal, we calculate criterion function. So the main program works on the following way. At the beginning, we define initial values of parameters. Then the next step is to evaluate the criterion function C. This evaluation means actually the call of a MATLAB function. This MATLAB function starts the simulation. With this simulation, we obtain criterion function, which is calculated in a transient response. This criterion function is returned to the MATLAB main program, and then the optimization program calculates improved values of parameters. Then there is a question whether or not to finish the optimization. If not, we continue with next iteration. So optimization actually means that we perform several iterations. Each iteration means the improved values of parameters. When the condition of end of optimization is fulfilled, we finish the optimization procedure, and here the optimal values of parameters are available. and of course optimal or minimal value of criterion function. This is the problem in which we optimize the control system. In this case, the Simulink scheme has the control system. We have the controller, we have the process, and we have, of course, the feedback. This is the reference signal. This is the error signal. This is the control variable, and this is the controlled variable. The evaluation of the criterion function is made using the error signal and also the control signal. This criterion function is then returned to the main program. But the main program is just the same as before. At the beginning, we define initial values of parameters, then we evaluate the criterion function calling a MATLAB function which starts the simulation. Then the main program calculates the improved values of parameters, and then if the optimization condition for end is not fulfilled, we go to the next iteration. But if the end condition is fulfilled, we finish the simulation, and then the optimal values of parameters are available, and of course also the optimal value of criterion function. This slide shows the possible criterion function. This is integral square error, integral time square error, integral absolute error, and integral time absolute error. So all criterion functions are integral functions, and they are using the error signal. Sometimes we used square of the error, sometimes we used multiplication by t. T is the independent variable. Sometimes we use absolute values of the error signal. The squaring and absolute value is needed especially when the error signal is oscillating in the transient response. That means that it has positive and negative parts. The multiplication by t means that we weight more the later part of the transient response. And this criteria is specialized for control systems optimization. In this criterion function, we use the square of the error signal, but we put into the criteria also the controlled variable. And this picture shows the criterion function, which is of this shape. And with regard to this shape, the selectivity is very important. This shape shows good selectivity. This means that in some iterations, we can easily find the optimal solution. In the optimal solution, we obtain the optimal value of the parameter, but we also obtain the optimal or minimal value of the criterion. Constraints are also sometimes introduced in the optimization procedure. Typical constraints are, for example, limited operating range of an actuator or maximal overshoot of a controlled variable. The optimization algorithm must calculate such optimal parameter values that the constraint conditions are not restricted. The conditions for completing the optimization are also important. Optimization ends if the prescribed number of iterations is reached. I explained before that one iteration means one improved set of optimization parameters. But optimization ends also if the change in the criterion function between two iterations is less than the prescribed threshold, or the optimization can end also if the change in the norm of parameters between two iterations is less than the prescribed threshold. Let's say some words about the optimization in MATLAB Simulink environment. We use optimization toolbox. In this toolbox there are many unconstrained methods and constrained methods, and in our example we will demonstrate the fmin search function. This is multidimensional nonlinear optimization using Nelder-Mead method. This slide describes fmin search function. The function has 3 input parameters and 2 output parameters. The input parameters are the following. Fun. This is the name of the MATLAB function which calculates criterion, in single quotes, without extension. In our concept, simulation is used for criterion evaluation. Therefore, Simulink model with sim command is executed. x0. These are initial values of parameters being optimized. And options. Options, this is the vector for configuration of optimization. It is set by optimset command. This is one example how we use optimset command. In this example, we define 2 ending conditions. 50 iterations is one ending condition, but the optimization ends also if the change of the criterion is less than 0.1 in the last iteration. This is this combination. With the command display iter, we define that some data are displayed during optimization. The results of the optimization are the output parameters xopt, this is the vector of optimal parameters, and copt, this is the optimal minimal value of the criterion. Here the MATLAB function for criterion function evaluation is described. The name of this file is fun.m, and this is the headline, the name of the function, the input parameter x, this is the vector of parameters for optimization, and the output parameter f, this is calculated criterion. The function has the following structure. At the beginning, initialization of Simulink model parameters x with current optimal values, then start of simulation with sim command. The states, outputs, and some other variables are stored for possible later calculation of criterion. The calculation of the criterion, this is actually the evaluation of the variable f. It is usually calculated with integration, but can also be calculated on the basis of some other simulation variables. Simulation configuration vector must also be properly set. This is an example how we define with simset 2 variables src workspace and dct workspace. We put them to so-called current values. I will not explain in details what does it mean, but this command can be used as a kind of template. It can be put on all optimization programs.